Okay, so today is kind of like our first official lesson where we actually go through new material. So today we will be learning about conic sections. So let's just go straight ahead into it. And I don't think everybody's here yet, but hopefully they show up later on, but we'll just start. So let's see here. The schedule, first we're going to go over circles, right? But since circles are part of conic sections, and some people are not too familiar with circles, since we never really went into depth with circles. So, we'll review circles, do some practice problems with it, and then we'll go over a new definition of parabolas, right? And then we'll also go over practice problems for those. And then we can go over any questions that you have, and that'll be the lesson for today. Okay, so first we're going to go over what analytic geometry is. So this is the definition, so make sure you copy this down. Analytic geometry. Okay. Is the study of geometric objects using algebraic techniques. So, study of geometric objects using algebraic techniques, right? And studying conic sections is a part of analytic geometry. So since algebra is very important and we use algebra in a lot of different mathematical fields, in geometry we use it a lot. So, and generally this guy, Descartes, is usually he's French, by the way. French philosopher and mathematician, is usually recognized as the founder. Is the founder, right, of analytic geometry. So that is analytic geometry, and today we will be going over conic sections. So you might be asking yourself, what exactly is a conic section? So let's go over what a conic section is. A conic section is basically any figure that can be obtained by slicing a double cone. The four conic sections we will cover are a circle, ellipse, parabola, and hyperbola. Let me just write that down. Make sure you copy it down too, especially the names of the conic sections. And also, to visualize this better, you might want to actually like copy down the diagrams I'm about to draw. So make sure you do that too. Right. So the conic section is any figure that can be obtained by slicing a double cone. Now, what is a double cone? I'll go over in a second. Okay, so a double cone is basically just looks like this, right? A double cone is basically this, right? It's two cones stacked on top of each other, and any figure, right, that can be obtained by slicing this double cone is basically a conic section. So let's look at our first slice possible here. So how about, since we can get four different figures from slicing this double cone, does anybody have any suggestions on how we should slice this in order to get a conic section? So does anybody have any suggestions on how to slice this? Yes, William. How do we slice this? This double
Maybe
cone
we could slice it as a parabola.
as a parabola. How do we slice a parabola out of this? So basically, if you imagine this, that we have a double cone, right? And we use a piece of paper and we slice it, right? And whatever shape in on that piece of paper is a conic section. So before you give any suggestions, I just want to point out the easy one, right? The easy one, you take this piece of paper, right? Take this piece of paper and you slice it horizontally. And if this is completely horizontal, meaning a 90-degree angle perpendicular to the ground, you have a circle here. You sliced out a circle, and that's our first the conic section. So that is a circle. Okay, William, what's your next suggestion? How do we slice a parabola out of this thing?
Um,
If we can slice it horizontally, can we slice it vertically?
yeah, I think so.
Right. So the thing is, we can slice it vertically like this, right? We get something like this. We slice it vertically, right? We have a piece of paper here, right? We just slice it like this. And as you can see, if you can visualize this, actually, I'm gonna use a different color here so it's easier to visualize. Use dotted lines or something like that. Yeah. So maybe yellow. So if you just slice it like this, okay, now you slice it like this, right? Then you see the figure we get is something like this, right? It's something like this. We get something along the lines of this, right? Okay, so let's use red here. We get two parabolas when we slice it vertically because this is completely vertical and that means it goes through both of the cones at once. And what is that called? It's actually not a parabola. It's called a hyperbola. The second thing we have here is a hyperbola. And don't worry if you don't get it. This is quite abstract, right? I'll actually go over the graphs of what they actually look like on a XY coordinate plane later. So how we actually get a parabola is not directly vertical or horizontal. So can you think of any other way to slice this cone to make it a parabola?
Maybe slice it diagonally.
Right, diagonally. So that's basically the only choice we have left. So one thing
What?
is we could slice it diagonally through an entire cone and we get something like this. This is one method. We can slice it. So let me change color again and hopefully you can see this better. Right, we get this. So if we slice it diagonally like this, it's not a perfect circle. If we slice it horizontally, it's a perfect circle. But if we slice it diagonally, here's what we get. We get an ellipse. It's basically an ellipse is an oval. So we get an ellipse here, and you can see this, right? This one is pretty easy to visualize. So we get an ellipse here. And the fourth one more way to slice it diagonally is we can slice off the tip here. For example, like this, right? So let me draw it better. You slice off try to slice off this tip here, right, of the cone. We get something like this if you put our piece of paper here, then the shape that we get on the paper is a parabola. Okay? Because that's the tip of the cone, right? So our fourth conic section is the parabola. So with that aside, you all know what a circle looks like. You all know what a circle looks like, right? And you also know what a parabola looks like. So what exactly does an ellipse and a hyperbola look like? So as you can see, this is the hyperbola, right? When you slice the cone, the two cones vertically, right? On a xy coordinate plane, it would look something like this. The two sections, right? Or it could be left to right, but it doesn't matter, right? This is basically what a hyperbola looks like. Basically, you can think of it as a double parabola, right? So it's just two parabolas, except they're reflected. Basically, one parabola reflected, right? And you can actually graph that with a general equation. So that's a hyperbola, and its general equation is actually more similar to the ellipse rather than the parabola. It's more similar to an ellipse than a parabola. And you'll learn later about the general equations and that kind of stuff. Now, ellipse, I guess it's also decently easy to visualize because it's just an oval. When you think of ellipse, think of an oval, right? So it's basically like a circle, except it's either long or wide, right? And there's also a general equation for that too. So hopefully everybody was able to know why this is called a conic section and that kind of stuff, right? So now we can review on circles, but before that, are there any questions? Are there any questions or anything confusing about the conic sections or the the introduction to conic sections? Any questions? I'll take them right now. If there are no questions, then I'm going to go to circles and review those. Right. So before we do anything with circles, we should probably also figure out or review the midpoint formula and the distance formulas because we'll also be using those later. Okay, so midpoint formula. Right? And these are the proofs of these are pretty pretty intuitive, right? So you don't actually need to write like a formal proof for these. Once I draw like the dagger, you'll be able to understand pretty well. So the midpoint formula states that to find the midpoint of a segment, you need to average the x and y values, right? You average those x and y values, then you get x1 plus x2 over 2 and y1 plus y2 over 2, right? And the distance formula is basically Pythagorean theorem, right? Distance formula. Right? Distance formula. And that is used to find the distance between two coordinate points, and d is going to be equal to square root of x1 minus x. No, let's do x2 minus x1 x2 minus x1 squared plus y2 minus y1 squared, right? So, who knows how to prove these, or at least draw them out, right? So, how about who wants to volunteer to try to figure out how this works, like prove this, right? You can volunteer. How about Kaylee? Kaylee, can you help me on this?
Okay.
So you don't actually need to give too much of a formal proof. Just make sure we actually understand why this works. So in midpoint formula, how do you think? Why is it true? You have a segment here. This is x2, y2, right? And this is what? x1, y1, right? So how do you actually visualize this?
Because if you have those 2 points across each other, then like you only have to find half the distance of the entire thing. So, and then we're just working up. You can kind of like make it like a triangle and then work from
Yeah,
there.
that's okay. So that's the main point here. Just make it a triangle. Whenever you're proving things on the coordinate plane, always draw a triangle because triangles are easy. Triangles, you have so many formulas for triangles. Well, of course, you're not going to use any of them, which is simple proof. But just in general, always draw a triangle first. And because you can use Pythagorean theorem, you have midpoint theorems, you have everything, right? So once you draw this triangle, I mean, do you even need to? It's not that hard. You can use like obviously use similar triangles and congruent triangles. You can write a formal proof on this because you have the same angles here. Obviously, these are already similar triangles, and since these are congruent, then these two are the same. And because they are the same, you can divide by 2, and that is the midpoint, right? But we don't need to go too much into that because it's all intuitive. Now for the distance formula, same thing, right? Same thing. You draw the triangle. Right? You draw the triangle, and it's quite easy to see, right? It's quite easy to see. This is x2 minus x1. This is y2 minus y1, and obviously this is just the Pythagorean theorem. Okay, so that's basically our little review of midpoint formula and distance formula. Don't worry, I won't erase these completely. I'll put them up there somewhere. And then we can actually go over the equation of circle because I do see some new students that may not remember what is the equation of a circle. So we have, let's just put our formulas up here. This is the midpoint, x1 plus y1 over 2, x2 plus y2 over 2. Okay, so and we have d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Right. Okay, so now a circle. What is a circle? Circle is basically a set or a locus of all points in a plane that are equidistant. Equidistant meaning, of course, equal distance from a fixed point called the center. And basically, the fixed distance is the radius. Important things the only important thing here you take from this definition is equidistant from radius. That's all we need to find whatever, right? So I write this long definition. You don't really need to know, like, don't remember this. It's not that important. You know what a circle is, right? Same radius, all around, it's just equidistant. Okay, so basically, if you take our center to be point HK and an arbitrary point P on the circle is XY, and radius we take is R. How do we find the equation of circle? That's the main part. So let's just draw our circle here. Pretty nice. And we have C. Now this C in this case is the origin, but let's just say that it's HK. Because sometimes the center is not in the origin. It may be like 3, 4 or 2, 3, negative 1, 2, right? And this is our arbitrary point, P. P in this case, right, is XY. Right? So I'm gonna ask another volunteer. Who can prove the equation of a circle? Who knows how to find the equation of a circle? Who wants to volunteer to help me solve or find the equation of a circle? Okay, how about William? William, I think last time you also knew how to prove the equation of a circle. So can you do it again?
Okay.
All right, so if you don't know, I'll walk you through it. Don't worry. Okay, so the point is R is here, right? And what did I
Yeah.
say earlier? What did I say earlier? When you're on a XY coordinate and you're trying to find something, what do you draw first?
You draw a triangle.
Great. We have a triangle here. Now, what's the equation?
So
Well, we have to use our formulas, right? So we know that to get an equation, we need two equal values. Two equal values are the distance from C, the center, to the arbitrary point P and R. The distance CP is is equal to R, right? So how would we find the distance from P to C?
the distance from P to C. What?
We use the distance formula, right? So what
Yeah.
is it?
So there's the square root of x, x2 minus x1 to the power 2 plus y2 minus y1 to the power 2.
Yes, in this case, what is x1 and what is x2? Let's just say x2 to be x, right? And that's minus h, right? So what's the next
Yeah.
one?
Y minus k,
And that is equal to what?
and that is equal to d, which is r.
Right. So we square both sides, right?
Mm.
Since it's easier, nobody likes the square root. Nobody likes the square root. It's too complicated to have a square root anywhere. So we square both sides just to make it simpler. So this is the standard equation of a circle. Okay, that's all you need to know for circles. Now let's do some example problems. This should be nice. Okay, so first one, I'm just gonna have you do, right? Find the equation of circle with center 3, -2, and passes through the point 1, 1. So we have a circle here with the center at 3, -2, and the circle also passes through the point 1, 1. How do we find the equation of this circle? Right? I'll give you a couple moments to do this. Should not be too hard. Okay, let's go over this one. This one should not have been too hard. So let's find a volunteer. Who wants to volunteer to solve this problem? Let's see who answered. Again, okay. Sophia. Okay, Sophia, can you help us to solve this? Are you willing to?
Okay.
So how do you solve this?
So because the center of the center of the circle is 3, -2, you can plug that into the formula for the circle, which would be x minus 3 parentheses squared plus y plus 2 parentheses squared equals r squared.
Okay, very good.
And because that passes through the point 1, 1, you can plug the point 1, 1 into that equation. So it'd be negative 2 squared plus 3 squared equals r squared.
Very good.
And then you
So
just solve for r.
yeah, okay. This is 13. So obviously r is equal to square root of 13. But do we really need to find r itself? A lot of times you don't actually need to find r itself and simplify square roots and that kind of stuff. You just need to find r squared to find the equation. So it's just x minus 3 squared plus y plus 2 squared is equal to 13. So it was that easy. Or you can use the distance from it to find the distance between these two, because that's also radius, right? But same thing, right? Okay, so now let's go over our new definition of a parabola, and this can be quite confusing, right? So please make sure you listen up, right? So let me see here. Our new definition of a parabola, right? New definition is the set of all points on a plane that are the same distance from a given point called the focus and a given line called directrix. Now, let's see here. So I'm going to draw the graph, right? So of course, this is what I call more of a geometric definition. So a squared plus bx, ax squared plus bx plus c. Now this is a more algebraic definition of a problem, but this is more geometric, and we use them interchangeably. Like sometimes this method is more useful, and other times you use ax squared plus bx plus c just fine. So let's see here. We have the directrix here. That is a given line. And we have the focus here, which is a given point. This is the vertex. So immediately, you notice a couple of things. First, I'm going to tell you that the distance of the focus and the directrix from the vertex is called p, meaning that they're equidistant. They're equidistant from the vertex, and the vertex is basically the midpoint. It's the midpoint between the focus and the directrix. Right? So we have an arbitrary point P here, right? So this is kind of what our parabola looks like. And the P passing through this parabola, right? The P passing through this parabola is equidistant. Is equidistant from the focus and the directrix. So every point on this parabola is equidistant. Like here, it is equidistant from the focus and the directrix. Here, it is equidistant from the focus and the directrix. So every point here, you can draw this. So you don't need to draw this too much, just to make sure you have enough points to graph it. A lot of times we're ballparking here, so we don't actually need very exact sketch. So this is basically our new definition of a problem, right? So are there any questions on this, on how to do this? Right. Once you really learn about once you know that the vertex is just midpoint between focus and the directrix, and the distances are equidistant, it doesn't seem that challenging anymore, right? So it's quite easy actually. And a lot of times when you're graphing it, it's much more easier than using the normal method with ax squared plus bx plus c. So now we go to our general formula. So we have a couple of things here that we can do. And basically the unique part of this new definition, the unique part is that we can draw sideways parabolas now. So our first position here, is going to be f at 0p, and the directrix here at y is equal to negative p, right? So this is a normal parabola, what you would expect, right? What we've done. And again, notice how they're equidistant from the vertex here. The distance is always p, right? So our second position here, also very, very normal. This is an upside down parabola, right? We see that all the time. We graphed that, we found the equations for that, right? We're very familiar with that. And this time, notice how because it opens down, the directrix is always behind the parabola or behind the vertex, and the focus indicates which way it opens, right? So the focus here is going to be 0, negative p this time. Directrix is y is equal to p. But now we get into some things you don't really see that often, and that is basically a sideways parabola. So we can have a sideways parabola like this, and it opens right. F is equal to p0, and the directrix here is x is equal to negative p. You can also have it open left. Just opening it left means the focus is to the left of the vertex. F is equal to negative p, 0, and the directrix is x is equal to positive p. And p is always going to be a positive number because it's the distance, and distance cannot be negative. Right. So what are the actual general formulas for this? But before that, are there any questions about how this happens? Are there any questions? If there are no questions, then I will continue. So this first one, where it opens up, is x squared is equal to 4py. Where it opens down is pretty self-explanatory, right? It's x squared is equal to negative 4py. Because it's negative, it opens down. Now, the difference here is when it opens sideways is y squared is equal to 4px, and y squared is equal to negative 4px here. So instead of having x, actually y as a function of x, basically here y is equal to f of x, right? Because x is squared. So instead of having y is equal to a function of x, here we have x is equal to a function of y. And because of that, we can then have something like this, and that is a sideways parabola. We switch the roles of x and y. This here, y is squared, not x. That's how it is sideways, right? So that's basically the general formulas. So make sure you know how this works. When it opens sideways, which is the odd case, right? It's weird when it opens sideways because we've never seen a parabola that looks like that, right? And you know that is when y is squared, right? So when it looks like the normal parabolas that we usually deal with, opening up and down, right? That's when x is squared. And it's pretty self-explanatory when the negatives are included. When it opens left, there's a negative, negative 4px, and when it opens down, it's negative 4py. So it's pretty self-explanatory, pretty obvious there. So now let's do some examples, and hopefully you know how to do things with these. Next time we'll go over what happens when the vertex is not at 0, 0. Because this is a parabola. These equations are when the vertex is at 0, 0. So it's very, very simple. But next class we'll go over ones that are not at 0, 0. So let's see here. Number 1 is graph y squared is equal to negative 8x. Okay, so I'll give you a moment to do that here, and we'll get back to you. Right. Okay, let's go over this one. So, I hope everybody took a chance to go into their notebooks to try to graph this, or at least remember the formulas and try to graph this. So, who can volunteer? Let me pick on someone. Huh. How about Brendan? Brendan, do you know how to graph this? No? Okay. How about Eric? Eric or William. Okay, William. Go ahead.
So for this, wait, do I just like do I just do like points, like plot in points for x and plug in values for x and y, or should I just do the focus and directress
Yeah,
for
do focus and directrix. You can't always plot points. Yeah. Okay. So first of all, what kind of equation is this? It's y squared is equal to negative 4px, right? And what does that tell us? What does that open up to?
to the I think to the left.
That's good. It opens up to the left. And now we just find p. We just find p.
What?
So yeah, we need to find p. So how do we find p here?
Is it 2?
2. Very good. Because that's very easy. That's very easy. Because negative 8 is equal to negative 4p, right? P is equal to 2, right? So we know the vertex. You know the vertex at you know the vertex is at 0, 0, right? So if P is 2 and it opens left, which direction is the focus at?
The focus is on the left. Like and the directress is on the right. So the focus is negative 2, 0.
Okay,
And then the directress is 2, 0.
very good. So wherever it opens, right? That's where the focus is. If it opens left, the focus is going to be left of the vertex, right? So then we need to find some points. So we can approximate just about where a point is because the distance is about equal, right? And we also see a point like right here. Or we have like a point here, a point here, you have here, right? So they're basically equal. Basically, these are all equal here. Right. Okay, but remember you don't have to do it that exact. I just need you to remember how to find focus and directrix. So that's how you graph the parabola due to this with this equation. Let's do one more. So the second one, you're writing an equation. Writing equation, right? Writing equation. The second one here, of parabola with vertex and 0, 0 and focus at 0, 2, right? So yeah. So find P and then you can write the equation, right? So I'll give you a couple moments to do that too. Okay, let's go over this one. So we have a couple of oh yes, Brendan. Yeah, I did call your name for the last question. But if you're in the car, that's fine. Okay. Anyways, William, y squared is equal to 8x. Okay. So, William, can you help us on how to do this again? So this one is also pretty easy, right? So we know the vertex is at 0, 0, and the focus is at 0, 2, right? So
Yeah.
how does it open? Up or down or right or left?
It opens up.
Right? Because focus is up, right? So the directrix must be below. So what is P?
P. I think P is 8
8?
or
Are you sure about that? It's a distance between the focus and the vertex, right? And
oh
what is the distance? It's
it's
2, right?
4.
4?
Oh, I mean 2.
Okay, okay. So we know it opens up, right? So we just need to find P. And we know it opens up. That equation is equal to 4py. X squared is equal to 8y, right? So make sure you always find P. I don't know how you got 4 or 8, but make sure it's just the distance, right? It's just the distance between the focus and the whatever, the vertex. Okay. So those are all the examples I have for today, and I'll post the homework shortly, probably tonight or tomorrow morning onto the Google Classroom. So make sure you start working on that, and it is due next class, right? Okay, I'll see you. I'll see you next time, I guess. I'll also post this recording. Okay.